Okay, it's time for the lecture number 4. In this lecture, we'll be discussing the current loop and the current loop design. In the previous lecture, we saw the block diagram representation of current mode control. So there are two feedback loops. Okay, let me quickly go back here. So this is the block diagram representation of smooth signal modulable converter. So this is current loop. Okay, this is symboled as Ti. I is current, and this bigger one is TV. Okay, first we'll be talking about this, and later on we'll discuss TV. Okay, so in this lecture number 4, we go through the details about this current loop, definition of the current loop, and design procedure of current loop. And based on this, I'll explain the PWM waveforms of current mode control, which is very important to understand the control scheme of this converter, PWM converter with current mode control. Okay, so this is obvious. Okay, this is current mode controlled converter. So when you are talking about the current loop, this voltage loop is disabled, dead. Okay, so assume there is a switch, and switch was here. There is the regular voltage mode control, which employs this inductor current feedback or switch current feedback and output voltage feedback all together. Okay, if this is switch is here, and this voltage constant DC is connected here, then this control voltage is fixed at DC. Okay, in terms of the AC signal is 0. Okay, so this is the current loop as defined in this situation. Okay, so when you are talking about current loop only closed or current loop only, you are talking about this configuration. Okay, voltage loop is dead, disconnected, and this fixed voltage is applied to here. That is the current loop only considered. Okay, with this condition, so you are not caring about this and just taking a look at this, and here this control V cone is 0. Okay, but this D hat is here, and the D hat will be changed to IL hat, and IL hat will be changed VI hat, and it will go here. So Ti is the loop formed by this current, additional current feedback. Okay, so this is the definition of Ti. Ti is this transfer function from here to there, which is GID in notation, and the gain from here to there. Okay, so I'm sorry, here VI should be there. Oh, this is okay. This is the IL hat. Okay, same thing. Okay, so I hat is multiplied by this, and it is fixed with this lamp. Okay, then it goes like this. Okay, so feedback loop is only this part. It's a gain of functional block. This and the gain of this and the gain of from here to there. Okay, so gain product of feedback path created by inductor current feedback with negative sign in front of that. Okay, I forgot to write that down, but originally there is a minus sign in front of this. The reason for this is obvious, right? Because you already have this minus sign. So to make the result positive, you need an additional minus sign here. Okay, so actually the minus gain product of feedback path created by inductor feedback. Okay, so negative is necessary here. You understand this, all right? Okay. When you are reading some book or some document from the company or industries, you will see with control voltage constant. Okay, that is this case. When this kind of configuration, this V-con is constant. V-con is this one. Okay? This AC component is 0, only DC is connected, and that is constant. That is the meaning of a fixed V-con. V-con, this capital letters, that is the one implication. And the meaning of this voltage feedback is broken, disabled. That means there's no output regulation. You are not caring about the output about this. We don't have any interest in this, okay? Maybe this voltage can be varied, but we don't care. We are only interested in this gain product. That is the implication of PI at fixed V-con, okay? Sometimes there is this feedback, this voltage feedback, the output voltage regulated, and some people, some industry people, they use the fixed out voltage. Fixed control voltage. Control voltage is never fixed unless the situation, okay? But in the steady state, with the voltage loop closed and the current loop closed, and that situation is shown here. This is a ramp signal. So I'm using voltage mode control to simplify the diagram, but you can extend this argument to the current mode control by modifying the current mode control waveforms. But this is the example with the voltage mode control. This ramp signal fixed, okay? Then this control voltage is not fixed, okay? But it contains this sinusoidal oscillation at the frequency of switching frequency, okay? That occurs always. If you simulate your closed converter and you expand out the waveforms here, this voltage, the control waveform looks like this. They are varying, sinusoidal waveforms, but this point is fixed, okay? They have sinusoidal disturbance, okay? But disturbance is adjusted to have the same point at every switching cycle. Then that maintains the duty ratio constant. This is the condition for the steady state. Duty ratio dt is fixed at DC value. For that, this can be varied, but the moment intersecting this red curve and the green curve is fixed in every switching period. That is called also constant V-con, all right? The industry people, they mixed up these two things, okay? So sometimes it's very confusing, all right? So distinction between them should be made, but still they are using this one, constant control voltage. I don't know this one or this one. It depends on the paragraph, the content of the entire sentence, okay? Can be either this one or either this one, okay? Okay. So we define the current loop as the gain product of this, and this one with disconnected. So the control voltage coming here is 0. Okay? No control voltage coming in because it is cut in the AC sense, or it is clamped at DC value. Okay? Then this current loop is a product of these things with minus sign in front of this. So this is this expression GIDSRI times FM prime. Okay? And the GIDS is duty ratio to inductor current feedback. This is a general expression. And for the different converter topologies, you should have different values of this. This is what? This is the current sensing network gain, and this is the modulator gain for the current mode control. Okay? Then there are there are two constant, three constant. This is a constant, this is a constant, this is constant. Everything is fixed. Then this becomes Ki. Here is a 1, 0, and here is a double pole. Okay? Expression of double pole is the same as the voltage mode control case. Okay? It can be different from the buck boost, okay, buck boost, okay? But it has the same pattern, and the Ki is product of three constant, which is this. Okay? And asymptotic plot of this is extremely easy. Okay, take a look at this one. There is a Ki DC gain, and there is a low frequency 0. This comes first usually. So it goes to the positive 1 slope at this double pole frequency. The slope is changing by 2. Okay, then plus 1 slope becomes minus 1. It reduces to the minus 1 to here, and forever according to this. Okay, and it will cross somewhere in the middle. It crosses the 0 dB frequency, and this is extremely important. The loop gain crossover frequency omega Ci is shown here. This is the most important parameter in current mode control. Okay. Later on, you will understand this. The designing the current mode control is selecting this one. Selecting this one. Okay. So eventually, current mode control is determining FM, determining SN, and determining this one. They are same thing. Okay. They are same expression, same statement with different expression, and the only problem is determining this. I told you in the previous class, the only one you can change is slope of external lamp in current mode control. That statement is the same as the only free variables in current mode control is selection of this point. Okay, they are same command, same statement, and only one parameter is available for the different current mode control design. Okay, and take a look at this. This is 0, right? This is horizontal line, and this is plus 1 90-degree phase, and this is minus 1 slope, minus 1 90-degree phase. Okay, that means what? This is stable. Okay, only current loop is closed. You are employing the negative feedback, but that feedback path is inherently stable with 90-degree phase margin. What is that? You cannot make this loop unstable, right? However, you increase this value, converter is always stable. This without this is stable. Okay, that means there's no sub-harmony oscillation going on here. Okay, so this is inherently stable with 90-degree phase margin when sampling effect is ignored. We ignore the sampling effect. Okay, so sampling effect is ignored. This is extremely trivial. So people, they don't analyze this. Okay, there is no literature, papers, or in the textbook. They just ignore this. Okay, so some people, some engineers, they think current loop is already there, or they can design arbitrarily. That is absolutely wrong. The most important design parameter is selection of this one. Okay, so this is so simple. So you don't have to simulate this. This is obvious, right? This is obvious. What else this can be? Okay, so there is no need rigorous analysis. They don't simulate this, or they don't measure this. Measuring is possible, but not that simple. Okay, because we are talking about the current disturbance, but you don't have to measure. You don't have to simulate. This is very simple. Okay, but if you include if you start thinking about the sampling effect, situation is entirely different. But in classical analysis, we assume sampling effect is totally ignored. We even don't think about that. Okay, there is no sampling effect at all whatsoever. Then this is always stable. Okay, and later on, or you can figure out this if you increase SE, if you increase this slope of compensation lamp, then you are decreasing this, right? You are decreasing this, okay? No. You increase this, or you are increasing this, then this whole thing will be decreased. Ki will be decreased, okay? That means you increase this larger SE, then this current loop will becomes this, and you increase SI further, it becomes like this, okay? if we increase further, this current loop will disappear from the converter dynamics. That means what? You have structure of current loop. You have current sensing network. You have external lamp employed. But in terms of dynamics and the circuit operation, this is just what? This is voltage mode control. Only this loop is zero because the magnitude becomes very smaller. It disappears below the 0 dB line. It's gone. Then what? You only have this is what? This is voltage mode control. Okay. External lamp is still there somewhere here. So converter becomes voltage mode control. Even you are assuming you are using current mode control. Your converter has a structure of current mode control. You have a current sensing network. You have the compensation lamp. But still, that's not a current mode control. That is the voltage mode control. Okay. Then how you can know this? You don't have to plot this. Okay. This is obvious from this simple sketch. You know this. Okay. And if this crossover frequency way below this, that means current loop gain is too small, and converter is almost the same as voltage mode control. And you confirm that from the performance of converter, frequency domain performance, loop gain plot, output impedance plot, audio susceptibility plot, and the transient response, step load transient response, and the step input transient response will be different from the case of the voltage mode, from the case of the current mode control. We will be discussing the detailed shape, structure, dynamics of current mode control later. Okay. Then, for this case, your response of your converter will be way different from the prediction of current mode control. Then, this SE is too large, and I'm just using the voltage mode control. Okay. You don't have to see anything. You don't need to see. This is so obvious. Okay. So I wrote down here the Ri and Fm prime. So this Ki. This is determined by power stage transfer function, and the Ri is current sensing network. This magnitude of this is determined by the maximum value of your inductor current times current sensing network should be smaller than allowable magnitude of your controller. Okay. If this product of P current and this becomes 100 volt, that does not make sense. Your PWM IC only can handle maybe less than 5 volt. Okay. So this Ri is determined some hardware constraint. Okay. This trick of the PWM IC and this trick of the maximum value of your inductor current, then the only parameter you can play with is this SE. Okay. So this Ri and or this FM, actually FM prime, and if this current sensing network gain is determined, this is determined, only parameter you can play with is this slope of compensation lamp. Okay, so this indicates there is only one free parameter when designing this one. Okay, they are not independent variables. Okay, you determine this is determined, then only remaining undetermined parameter is this one. Okay, and excessively large SE sweeps out. Sweeps out means it kicks out all the contribution of inductor current feedback, and your feedback is virtually a voltage mode control. Okay, you understand this, right? And the sign of the excessively large, this compensation lamp, can be seen here. Okay, usually they don't simulate this. Okay, that is so simple. You can simulate that. Let me show one example here. Okay, this example is taken from the Ray Diddley, that guy. Okay, that famous guy. Okay. And I took this one from his dissertation this morning. You don't have this. Okay, this is the most recent one. Okay, so there are comparison. This is a current loop. Okay, This is in this plot, he used the Middlebrooks FM expression. But this gain, and it has +1 slope, double pole, -1 slope, and the phase is this one. According this converter, this current loop is always stable, regardless of this 0 dB crossover frequency of current loop. But this one is experimental result. Experimental result, it shows something strange. It is going up like this, okay? But he failed to measure that. He stopped here, and the phase of this current loop is decreasing this much. At the half-tone switching frequency, it shows this additional 90-degree phase delay. With this, the loop can be unstable. Okay? So this is the sampling effect. This is coming from the sampling effect. So now we are ignoring sampling effect. Okay? And this is the magnitude of the sampling gain. Sampling gain is something I don't explain you yet. Later on, I'll explain this. Okay? The gain at low frequency gain is this one. This one. This gain like this. Then it goes like this. Goes like this. Okay? It goes to the infinity actually. And this is the phase. And the phase drops by 90 degrees at the half-tone switching frequency. Half-tone switching frequency is very important. One here, it has big significance. That is called the Nyquist frequency in discrete time system or sampled data system or in communication system. Okay, that is just simply half-tone switching frequency. Okay, so why they are using some Nyquist frequency, something like that? Okay, simply half-tone switching frequency. Okay, there are 90 degree additional phase delay is coming in. Okay. This is the effect of the sampling. If you ignore this, then you don't see this. Okay? You don't see this, right? This is very familiar to you. Where did you see this? High frequency oscillation of modulator by Middlebrook using describe function method. Okay? You have seen something like this. Okay? At that time, you have seen this one. Okay? But this is the TI, and the loop gain we are talking about is loop gain that is similar to the voltage mode case is this one. This one is called the outer loop gain, and the TI is coming. This is the loop gain seen at the output side of this converter. TI is coming in the denominator. So you have seen this, and here this is upside down. Is coming up here. Okay? So if it goes downstairs, it is doing like this. This is the sync function. We have seen the Middlebrooks modulator gain analysis. That was the voltage mode control. So even voltage mode control has this sampling effect. Okay, but sampling effect is not that strong there. But in the current mode control, sampling effect is rather strong. But we are totally ignoring sampling effect. When that is fine. When crossover frequency is below this one, okay? We are is below this, then there is no this phase additional phase delay, no this strange behavior, then we are safe, okay? So in the classical analysis, they ignore sampling effect totally, but they suggest the crossover frequency, loop gain crossover frequency. Current loop crossover frequency stay within this bound. Okay? So by limiting the omega Ci is current loop crossover frequency. That is the largest crossover frequency in current mode control, and this frequency falls below, well below the Nyquist frequency. With that constraint, you don't have to worry about the sampling effect at all. Okay? That is the way of doing all the business without any trouble in classical analysis. You understand this? Classical analysis is ignoring sampling effect totally. Still they are okay because they have hard destruction lower limit about this, don't go in the neighborhood of Nyquist frequency. Then you are still fine. Okay? So classical analysis is okay, perfectly okay, if this is observed. Okay? This is regulate the maximum crossover frequency of current loop is lower than this. Then you can even totally ignore sampling effect, and the classical analysis is as good as new analysis, or even in some cases this is very simpler, much simpler. Okay, and with this, the design of current mode control is even the case of the voltage mode control. I told you several times. In the previous lecture slide, we briefly discussed the sampling effect of the current mode control on the loop gain, current loop characteristic of PWM converters, and we found out that the classical analysis keep away from the issues of current mode control, sampling effect of the current mode control by placing the loop gain 0 dB crossover frequency of current loop at relatively low frequencies. Now we postpone the detailed issues about the sampling effect of current mode control later, and we come back to the classical analysis of current loop. This is the small signal block diagram of current loop. Okay, this is the small signal block diagram of current mode controlled converter, and this TI represents the current loop. Okay, and this is the plot of the current loop. Okay, and omega CI is 0 dB crossover frequency of current loop, and the 0 dB crossover frequency is located well below the Helpter switching frequency. We will be discussing this later in detail. So this frequency is less than switching frequency divided by 2. Okay, so we have 3 different curves. The difference between them is, this is the expression for the current loop, GIDS times RI. RI is current sensing network gain, and FM prime is modulator gain of current mode control. And we have different expression for the current mode control. So we have 4 different expressions. Okay, at least 4 different expressions have been proposed, and this is the FM prime 1, 2, 3, 4. Okay, so with different this FM prime expression, the only difference occurs at this value of the Ki, because the Ki is the magnitude of this current loop, and the current loop is multiplied by this. They remain the same. So by using different this current loop expression, the magnitude of Ki will be different, and accordingly the crossover frequency of current loop will be different. Okay, so here we analyzed this. When this D is assumed to 0.5, then FM prime 1 and FM prime 4, they are same. Okay, this is the largest value among this comparison, and this one is smaller, this one is smaller than this one. So when you select the omega Ci using this expression, this one proposed by FCB, this is the most conservative selection and or the safest choice among 4. Okay, if you assume this is the upper one is derived from this middle this Fred V expression of modulator gain. If you use other gains, then it will be smaller. This omega Ci will be smaller, so you are safer. Okay, so this is the most conservative selection or best choice in this case. Okay, but this difference will be very small, right? Assume this is very large compared to with this one, then effectively the impact of this one will be very small. Okay, so if this condition is met, if SE, slope of external lamp, is relatively larger than SN, then this difference will be very small. So it really doesn't matter which one you are using. Okay, if you use this one, that is the best selection in terms of the conservativeness of your design. Okay, so people claimed different expression for this modulator gain, but difference doesn't affect the design result that much. Okay, as you will see later, difference in here does not affect at all for the voltage loop design. So arguing the correctness of this or this is use this. Okay, basically use this. Okay, anyone can be used, but this one is the best one to be used here. I explained the reasons, many reasons here. Okay, so let's take a close look at the current loop design. So this is the current loop. Okay, so design theme is to place the TI crossover frequency omega CI at the predefined frequency. Okay, for example, omega CI will be located at 0.1 to 0.3 times omega S. Omega S is the switching frequency. Okay, so you know the region. Okay, so I explained in details about this at topic 9-2 in lecture 7. Okay, that is related with the accuracy of or validity of small signal modeling of modulator. And there is another more important reason is effect of the sampling. Impact of the sampling effect of the current mode control. Okay, if you select this value omega CI, any number in between here, then current loop design is fixed. You don't have any choice other than that. So that is the final decision. And the simulating this or analyzing this is unnecessary because this is so simple. So if you select this properly, some number with this, okay, we'll go to complete details about this. What is the difference between 0.1, 0.2, and 0.3? Sometimes you can go to until 0.5. What those changes will make to the result of your converter will be discussed later. Okay, so assume you select one typical value in between here, then this is the TI expression is this. Okay, GID expression is this one, and the KID is DC gain of control to inductor current transfer function. RI is what? RI is current sensing network gain, and the FM prime is modulator of current mode control. So they are all constant. This is constant, this is constant, this is constant, and you multiply these three constant all together. So you have another constant KI. This is pole frequency. This is zero frequency, and this is double pole frequency of power stage double pole. Okay, so you understand this, all right? So one expression is this one, KI is given by this KID times RI times FM prime, and FM prime is given here. This is the Fred series gain formula. Okay, then suppose you select this value, then you need to select this one, and this one will determine this, and this, then this they are known. Then FM prime is determined, and if this is determined, this SE is determined. Okay, so the only one control variable here is slope of external lamp. Everything is fixed by something else. Okay, so the optimal design is selecting SE properly. I think I told you once, if there is a machine which can change this SE continuously, and you use the machine and vary this continually, and you stop at the best point, that will be the best design. Okay, but we are trying to find out this one analytically. In engineering sense, that is the whole purpose of design, and that is the same as selecting this omega CI properly. Okay. Okay. So this is selected, then you need to determine this, As I said, if this is determined, this will be determined, this will be determined eventually. So SE is the final control variable, and you have the simple equation here. So this value is 20 log Ki, and the slope is +1. So you start out from here. So 20 log Ki plus 20 log omega ID to omega naught with 20 dB per decade slope, and the minus means this one, and from here to there with negative sign here, then this is the 0 dB crossover frequency becomes 0 dB. Okay, this is the log scale. You can easily convert these things into linear scale, and this is the equation of determining this and this. Okay, so you have two equations for same Ki. Then you can equate this one, number 1 and the number 2. So you can find out if omega Ci is determined, Fm prime will be determined, then automatically this one will be determined. Okay? So current loop design is so simple. Just selecting one number here as the end of current loop design, then everything will be determined according to this equation. All right? Okay. I'd like to emphasize this. So omega Ci as this one, 0 dB crossover frequency, is proportional to Ki, and Ki is proportional to this one. Okay, 1 over Se. So omega Ci is inversely proportional to 1 over Se. So if you increase the external length slope, then omega Ci will be reduced. Okay, the whole thing will be reduced. Eventually, you will losing all the benefit of using current mode control. Okay, again, for that case, you have the structure of current mode control. You have voltage current sensing network, external lamp, but functionally, but in dynamics, that becomes voltage mode control. That design cannot be applied boost and buck boost converter. If that design is applied to the buck converter, closed loop performance will be very poor. Okay? Right. So I marked here, this is equation number 1, and this is equation number 2, and the design procedure current loop is extremely simple. Okay? So this is the TIS current loop expression, and the KI is expressed like this. Okay, this is from the collection of all the coefficient of transfer functions. Okay, and this comes from the graphical analysis, frequency domain analysis. You have two different equations for the same parameters. So there is a good potential in these two equations. So first step is select Ti crossover frequency omega Ci in between this number 10 to 30% of the switching frequency. Okay, you know the reason, but the detailed discussion about this will come later. So this is very important and very critical step determining this. This will determine maybe 90% of your converter performance. Okay. All right. Then evaluate Ki. Then required. So you select this. Then you determine Ki. So Ki expression is here. So you use this. Okay. This is determined, and this is you selected this omega Ci, and this is determined by power stage parameter, and this is the equation number 2. Okay. And select the current sensing network gain. So this, the Ri is the current sensing network. This is the maximum peak current of inductor current. And the product of them is the peak value signal, peak magnitude of the feedback signal. That signal should be some the maximum value determined by the control chip or something else. Okay. So typically this value is Vmax is somewhere between, it depends on chip by chip, 1 to 6 volt, okay, maybe 1.5 or 3, 4, something like that. So if this is very large, then make this one slower. So the product then does not exceed this one. Okay, so this is a predetermined value, and here Vmax is the maximum allowable input voltage for the PWM block or PWM IC. Okay, then Ki is determined. Then use equation number 1. Then you determine Fm prime, modulator gain of the current mode control. Then Fm prime is determined. Okay, and this is the expression for the Fm prime. And from this expression is rearranged like this. Then this will determine the value of the SE. Okay, as this slope of this external lamp is always larger than this. This is what? This is the stability condition for the current mode control when duty ratio exceeds 0.5. Okay, the slope is absolutely larger than this one, so this is stable. Okay, it guarantees the stability of the current loop using this equation. Okay, this expression. Right. So here is one design example. This design example is coming later. Okay, again, but we introduce this. Okay, this is the parameters of the inductor, ESR of inductor, capacitor, ESR of capacitor, load resistor. Everything remains the same as the buck converter we used for voltage mode control. Okay, so we are using the same buck converter, one for the voltage mode control. Now we are using the current mode control for the same power stage configuration. Okay, and this is the current loop. This is the current loop. So we are talking about the current loop. So we open the voltage loop. So by positioning switch to this DC value, this is cut. Okay, the feedback is broken in small signal sense. So this switch is this position. That means this voltage loop is broken. Okay, so and structure of this eventually we will be using the current mode. This one. This is the 2-pole 1-0 circuit. Okay, so this is 2-pole 1-0 circuit. I think I introduced this some time ago. 2-pole 1-0 circuit. This is the standard compensation circuit for the voltage, the current mode control, applicable to all the PWM converters. Okay, so effectively, no, you don't have to cut here. Okay, this one is okay. This one is, but they are disconnected in the small signal sense. Okay, and the DC value of this is provided this, and this is the current loop. Okay, all right. Then this is the power state double pole frequency. ER star 0 is the 0 frequency of this one, of the duty ratio to inductor current transfer function, and the KID is DC gain of inductor. Duty ratio to inductor current transfer function is Vs divided by R. So this is 16. Okay, D is 0.25 because this is the 4 volt, and eventually this will be regulated if this is connected like this. Okay, we connected in this direction for the conceptual display of this for the voltage loop design. So this is 0.25 switching frequency, and the maximum value allowable to this chip is assumed 5 volt. Okay, and this is necessary to determine what CSN gain Ri. Okay, so peak value of the inductor current. So this is the minimum value of the inductor current, and this is the on-time slope times on-time period is the increase in the on-time period, and this is the peak value of inductor current. So this, you can determine this, right? Of course, the inductor current will be something like this. Inductor current is this one. Inductor current is this one, but you are using the switch current. Okay, so this average value. This is the on-time slope, on-time period, have to this increase, okay? So the peak value is 4.75 M for this case, okay? With this, we determine the remaining parameter for this. This is the procedure of current loop, okay? Select TI crossover frequency omega CI at 20% of switching frequency, this frequency. I'll explain reason why, okay? I'll explain the difference between selecting 0.1, 0.3, and even 0.5, okay? Then DC gain of TI current loop KI is given by this based on the equation. This was equation number 2, right? So this is equation number 2. We identify equation number 1 and number 2 here. Number 1, number 2. So we are using equation number 2 here. Okay. KI is determined as this one, 2.52. Okay. All right. Then go to this selection of the current sensing network gain. So current sensing network gain must be smaller than this number. This is the maximum allowable voltage, control voltage, or PWM voltage, and this is the maximum value of inductor current. So this is assumed to 5.0, and this 4.75. We calculate this in the previous slide, and this upper limit is this. So we select this number. Okay, something smaller than this is okay. Okay, this is dangerous. Then select some the margin. So I select 0.67. Okay. Then modulator gain is this is equation number 1, right? So this is design equation number 1. Equation number 1. Fm prime is determined from this equation. Okay. So Fm prime is this number. Then SE, slope of external lamp, is given by this equation, right? So then you plug numbers here. Every number is here. Then this is the slope of your external lamp, and this is the maximum value of your lamp signal, V lamp. V lamp is here, and this is the slope of external lamp, and this is modulator gain. This is This is current sensing network gain. This is some intermediate variable. Okay, so you finish the current loop design. Okay, this is the almost optimal design. You just select one number, 0.2, and everything is determined automatically based on this equation. Okay, you don't have to use any other number than this one. Maybe you use 0.3, then you will come up with different number. Following this, the exactly same procedure will produce different design output. Okay. Okay. This is kind of repetition. Okay. This is the power stage, and this is the voltage feedback circuit, which is configured as a 2-pole-1-0 circuit here. Okay. Again, this is connected to here because we are talking about the current loop, current waveforms. So that means Vcon is fixed at the DC value here. Okay, because this is connected to this. Okay, this will be better. The Vcon is DC value of this one. Vcon is Vcon, which is shown here. Okay, so this is Vcon, right? And control waveforms. This is a V lamp signal. So V lamp is generated periodically, and Vi is switch current. So switch current is sensed. Switch current is sensed and multiplied by this Ri. That is Vi. So Vi is IL or IQ times Ri is Vi. Okay. So dimension is voltage, and this external lamp is added to there. So this will be added. So this peak value should be this one. Okay. So everything makes sense, right? Okay. This is the graphical analysis, and I did one simulation, And the output of this is VQ switch drive signal, which is shown here. VQ, and this is, again, this is current loop, TI, and the switch is connected to DC, okay? When you are talking about the current loop, this should be DC, like this, okay? This is PSIM simulation. This is a PSIM file. This is power stage, okay? And this is the gain. This 0.67 is the CSN gain, RI. That signal is the inductor, the switch current or inductor current is multiplied by that number, 0.67, and result of that is connected to this here by some equation. So VI is coming here, okay? And the VI is mixed with V ramp. This is the height of the V ramp, which was 2.92 volt, okay? This is the DC value. This is what? V-con, okay? DC value of control voltage was 3.91, okay? I calculate here. This is the DC value of the V-con, I peak times RI, okay? This is the VI, and this is the what? This is the portion of external lamp added to the current sensing that, current feedback signal. So this is the duty ratio. This is 0.25. This one is the duty ratio. This is maximum value given here. Then number is 3.91 volt. This is the simulation result. Okay. I type this number here. Then the control waveforms is this one. This is the PWM signal. Okay. PWM. This is the VQ, and this is the VI. Okay. VI is this one. VI is this one. And this is the VI plus V ramp. And V ramp is this one. So this length and this length are the same. Okay. And this IL is inductor current. So IL is sensed and multiplied by current sensing network gain. Then that becomes this VI. Okay. The peak value is this one. Exactly this one. Otherwise, I'm lying to you. Okay. I lied to you. So this is correct. This is a correct waveforms. So current loop is working. Okay. Right? You understand this? Okay? So current loop design is extremely simple. Just a matter of selecting one number between 0.1 to 0.3 or from 0.1 to 0.5. Okay? So design of the current loop is just selecting just one number. Again, the current, the 0 dB crossover frequency of the current loop. Okay, so this is the end of this lecture 4.